So today we're going to talk about gears, pulley drives, and sprockets. Gears, pulley drives, and sprockets. These three powertrain elements transfer energy through rotary motion. They change the speed of the rotations, they change the directions, and they change the amount of torque available to do the work itself. So a gear. A gear train is a mechanism used for transferring the rotational motion and torque through the interlocking teeth. It's made when two or more gears are stuck together. It causes that motion, and that motion is transferred to the next driven gears. You got input, output, input, output, input, output, all the way down through your system. So you have mating gears always turn in those opposite directions. You got clockwise and counterclockwise. Idler gears allow gears to move in the same direction. So these two blue gears are both going clockwise. That red gear is going counterclockwise. When you mate them, make sure that just size and teeth are always going together when you're trying to create stuff. So gears, RPM of the largest gear is always slower than the RPM of the smaller gear. And gears interlocked together on the same shaft will always turn in the same direction and the same revolutions per minute. So looking at a couple different things and some terminology to use to try to talk about gears. There's a variable n, which is the number of teeth. There's the diameter, same as a circle, you got from one end to the other. There is the Greek lowercase symbol of omega, which is your angular velocity or your speed. And then you've got torque, which is tau. So how much torque's being applied. So we're going to go through when we look at the two gears. We've got input of 6 teeth, output is 12, so double. Diameter 2, output 4 diameter. So we had 1, 2, 3, 4, 5, 6. Count those, you got 12. Diameter 2, diameter out 4. Angular velocity or speed. We've got input 40, output 20. So that's inverse. Double, double, cut in half. So what are we going? We're going from a small gear to a large gear, so therefore we're going from faster to slower. And then torque. So what do we got with torque? Well, so gear ratios. Gear ratio equation to know. A gear ratio is equal to the number of teeth out versus the number of teeth in, the diameter out over the diameter in, and the angular speed in over angular speed out, torque out over torque in. So if we look at that, and we try to just do a little conceptualizing before we go ahead and do it, what happens as the output speed increases? Well, if this speed increases, everything else needs to decrease. So if you increase speed, you're going to decrease torque. If you increase speed, you're going to decrease size. So there's just a couple of different things to think about as we go through and we try to solve some problems and figure out what we want to do with a gear ratio and what can become of our system itself. So we got a compound or a gear train that's here. We're going to calculate the gear ratio. So we've got from gear A to B. So we've got our input, we've got our output. So we got 12 over 20, which is, reduce that down, you can go 12 over 20, 6 over 10, 3 over, we can go 3 over 5 or 0.6. Then we got an input B to output C. So we got 5 over 12. 5 over 12, divide those two, we got about 0.42. And then we've got an output D, input C. So we get 20 over 5, reduces down to 4 over 1. So just taking a look, big to small, small to big. So what's happening? We are decreasing speed, or decreasing size, so we'd increase speed. Decrease size, so we'd increase speed. Increase size, so we'll decrease speed there. Because if we go 5 here, we're only going 5 here. So one revolution here is only about a quarter of what's there. So what do we want to do? If we want to figure out what the total gear ratio is, the idler gears really don't matter. Let's prove that. We went ahead, we got a gear ratio, A to B, B to C, C to D. If we multiply all of those out, that gear ratio is 1 to 1. What's the gear ratio of output over input? 20 over 20 gives us just that 1. So those idler gears, all they did is change direction. Clockwise, counterclockwise, clockwise, counterclockwise. So A is going one direction, B is going that opposite direction that's there. So if we switch this out and we put 40 teeth here, output is 40, input is 20, we got a 4 to 2. That 4 to 2 ratio then is giving us a ratio of 2 to 1. So our gear ratio would be 2 to 1. So it takes 2 revolutions of this gear to make 1 revolution of that gear on the output that's there. So we're going to look at some compound machines, gear ratios. What are we looking for? For mechanical advantage, we apply torque and force. So the force out is mechanical advantage and your force is in. Your torque out is your gear ratios and your torque that's in. In a compound machine, the total mechanical advantage and gear ratio are the product of the components. So total mechanical advantage is the product of all of them. Total gear ratio is the product of all those. Mechanical advantage is calculating forces. Gear ratio will calculate your torque. So we've got a compound machine that is here. There's 3 different mechanisms. We've got a wheel and axle. So we have a wheel, a pink wheel, an axle of that shaft that's there. We have a gear train, pink to blue, and we have a wheel and axle. We have this blue gear and the axle of that shaft there. So we're going to go step by step. Number 1, we have a wheel and axle. So the distance of the effort, which is that 4, and then we have the distance of the resistance, which is that 1.5 radius on that gear itself. Divide those two, we got a mechanical advantage of 2.67 or 2 2/3. Second part, we have a gear train. We have pink gear input, blue gear output. So how do you find the gear ratio of 2 gears? Number of teeth out over number of teeth in. Out is 24, in is 60. 24 over 60 gives us that 0.44 tenths. Third set is the wheel and axle. The wheel and axle, we have got the input, that blue gear, the output, the axle itself. So the input has a radius of 0.6. The output has a radius of 4. So take 0.6 divided by 4. We get a mechanical advantage of that third mechanism being 0.15. So the total mechanical advantage from the other slides is the 2 2/3 times the 1500ths. So our total mechanical advantage is 0.4. So mechanical advantage is less than 1, meaning it takes more effort here than to go there. So that's 4 to 10. So 4 pounds of effort there. Or we got, 4 to 10. So for 4 pounds of resistance, it takes us 10 pounds of effort. Then gear ratio total. Gear ratio total is 4/10. So that means, what do we have? We've got, for every 4 rotations of this effort, there's going to be 10 rotations of that resistance. So now what do we want to look at? We want to look at some compound gear trains. Compound gear trains means that we've got the input. It's connected to an output. But then another gear is on that same shaft, which then is connected to an output of that third one. So the 2 middle gears share the common axle, and they rotate at that same speed. You can follow those 2 lines that go along. We are now going from a small gear to a large gear, so you can kind of see that change in speed that we're looking at. So that is called a compound gear train. So what is the relationship? We're going to look at in to out, in to out, in to out. So out over in gives us 4 to 1. We got this relationship here, out over in, which is 50 to 20, so 2.5. So what's the whole gear train itself? Well, we take the product of those two. We got 4 times 2.5 gives us 10. So that means 10 rotations of this small gear A gives us 1 rotation of that larger gear D. So that gear ratio of 10 to 1. Other thing we want to look at is belts and pulleys. belts and pulleys have the same type of formulas. Diameter out, diameter in, speed out, torque in. So, given some information, all those ratios should be equal to each other, so we bring them to a problem to try to solve. Given all that information, we've got input of speed, output of speed, input of speed, output of speed, all those relationships being 2 to 1. We are decreasing speed, so therefore we're increasing our torque. So pulleys and sprockets, what's better than the other? You can take a look at that. Pulleys uses belts. There's quiet, very few lubrication. It's inexpensive, but you can slip off of it itself. Sprocket, what kind of thing are you going to use? You're going to use a chain. There is no slip because it goes and hooks into the teeth that's there, but you've got a lot of friction that's created, so you got higher costs because you got to pay for the lubrication, and there's that noise that goes along with it. So that covers up our pulleys and our sprockets and our gears. Any questions, let me know.